As you see, metal, in this schematic, metal alloys are divided into two categories: ferrous and non-ferrous. What is ferrous? Ferrous means the main um, element is going to be iron. So the main element of those alloys are iron. But the main element is not iron. For example, aluminum alloy is one non-ferrous material. We will talk about this alloys in the next lecture. In the ferrous alloys, we have the steel and we have cast iron. In the steel, the amount of carbon is less than 2.11 weight percent. Less than this. But in the cast iron, the amount of carbon is going to be more than 2.11. Okay. In the steel, we have low alloy and high alloy. In the low alloy steel, we have again low carbon steel, medium carbon steel, and high carbon steel. All of these three steels are called plain steel. And these three, they have different amount of carbon in it, because of the carbon has a significant effect on their mechanical property. Therefore, steels are tailored to have a wide range of mechanical and physical properties. The principal or the main disadvantage of ferrous alloys is that they are susceptible to corrosion. But this concern can be addressed when we are dealing with high alloy steel, like stainless steel. In the previous lecture, we mentioned that steel is an iron carbon alloy, and steel are divided into two categories: low alloy steel and high alloy steel. Here we have FEC diagram, and this is pure iron. As we go here, the amount of carbon is going to be increased. At this point, the maximum amount of carbon here is going to be 6.67 weight percent. The first steel that we want to mention is a low carbon steel. The amount of carbon in that steel is 0.2 weight percent. We have four type of steel here. The first one is low carbon steel. Actually, we are mostly interested in three of them. The last one is not very applicable in industry. The next one is medium carbon steel, and the amount of carbon varies between 0.2 and 0.4 weight percent. The third one is high carbon steel, and we have carbon between 0.4 and 1 weight percent. The last one is ultra high carbon steel, has very limited application. Low carbon steel has many application. In that steel, it's not heat treatable because the amount of carbon is low, and you cannot form martensite. If you want to form martensite, the amount of carbon should be in certain amount, so the carbon is gonna be trapped in the austenite. Then you can form martensite. So, but here, because the amount of carbon is low, martensite formation is going to be very difficult. However, if you want to increase the strength of this low carbon steel, one way is to perform cold working. Cold working actually can increase the strength of low carbon steel. And the phases that are available that can be seen in the low carbon steel is a ferrite, and pearlite. I'm writing, this words by the mouse, so spelling is not, as good. There are several classification. This table shows a mechanical property of couple material, a couple of steel here, low carbon steel mostly, and this one is low carbon steel 1010, AISI 1010. We mentioned 10 here represent the amount of carbon 10. Here the amount of carbon is 20, right? So this has more carbon comparing, with this alloy. And here we see the strength of this material is more than the previous one, and the yield strength is more than again the previous, but the ductility dropped by 3%. What is it? Why it happened? The carbon actually increased. The main cause of increasing strength, and when the strength goes up, material actually when you add carbon, the material become harder, so the strength goes up but ductility goes down. What is strength and what is ductility? If you have a sample that you put in the tensile tester machine and you pull, for example, this is when you want to do the tensile test, you have to make a dog bone sample, and then you put this sample in a tensile tester, then you pull apart, then you get to know force displacement. This is force versus the amount of displacement you have. Then you can calculate a stress versus a strain. The stress means F divided by A, D minus D0 divided by D. So that gives you a strain. Then you can plot these components versus each other, and then you see this behavior. Up to here is the elastic behavior, then we have plastic. This is the strength of the material. When you add carbon, this strength goes up, but ductility is going to be lower. It means that this is corresponding to 10, for example, 1020. This is for material for a 1010 alloy. So this 1010 has a lower strength with the larger ductility, means it can be stretched more, but the other one has a shorter ductility. This length means lesser stretch it can go through, but the amount of strength went up. Okay, here we already mentioned that carbon is the principal alloying element in the plain carbon steel. We have three types: low carbon, medium, and high carbon steel. We have ultra high steel because it has a limited application. Then we are not mentioning it again in this slide. And then the manganese portion is going to be 0.5%, which is normal. The main application of low carbon steel is in automobile parts, or plate steel for fabrication, or railroad rails. And for the medium carbon steel, which has this amount of carbon in it, can be used for machinery component, crankshaft, connector. And for high carbon steel, which can be heat treated, these two can be heat treated, means that they can be harder if you do heat treatment. So heat treatment, in the heat treatment you can form martensite. Martensite is a hard material, so you can increase the strength. The application can be a spring, cutting tool, blades, and wear resistance parts. Another group of low carbon steel is called high strength low alloy steel, or HSLA steel, and this is very popular steel. They contain alloy elements such as copper, vanadium, nickel, molybdenum, and the combination of these elements can be up to 10 weight%. And because of these elements, we can do various processing techniques such as quenching, rolling, and this process can increase strength through promotion of a small grain size. As you know, the smaller grain size gives you higher strength. These materials are ductile, formable. In a normal atmosphere or environment, these steel are more resistant to corrosion than the regular low carbon steel that doesn't have these alloying elements such as copper, vanadium, and nickel. Another group of carbon steel is called the medium carbon steel, where we have carbon in the steel between 0.2 and 0.4 weight%. These alloy can be heat treated. We have various types of heat treatment, but the general idea is to quench the steel in order to have higher strength by making the grains smaller, or having more martensite in the material. Some of the alloying element that we have in the medium carbon steel is called chromium, nickel, molybdenum, which increase the capacity of these alloys to be heat treated. And when you do heat treatment, material might become stronger, but there is some disadvantage. You may lose ductility or toughness. Because the material have higher strength, we can use these alloy in gear, crankshaft, and railway wheels. Also, these material have a better wear resistance comparing with the low carbon steel, because of these alloying elements we have this material. The next group is high carbon steel, which is the hardest and the strongest because of the amount of carbon. we have a carbon between 0.6 and 1.4 weight%. These steel have a least ductility among carbon steel because of their high strength and hardness. They can be used as a sharp cutting edge because of, again, high amount of carbon in these alloys. We can use them as a tool and die, and they can have high amount of carbon, chromium and vanadium and tungsten. Some examples of this, the application of this steel is knife, razor, hacksaw, blades, spring, and higher strength wires. This plot shows the relationship between tensile strength and hardness as a function of carbon content in the plain carbon steel. As you see here in this axis, we have a carbon amount which increases from left to right, and here we have hardness. We have different hardness tests. One of them is a Brinell. This is a unit HB. We can have Vickers or other type, and this is the tensile strength. As you see, this plot, the y-axis is going to be here, and this one is this tensile strength. As the amount of carbon increases, the hardness goes up and tensile strength goes up, in the same order. This is another example of AISI designation for carbon steel. We previously mentioned 1010, which is a low carbon steel, but here we have 13, means manganese steel. If we have 20, it means nickel steel, or 31 nickel chromium, 41 chrome molybdenum steel, and the last two digits shows the amount of carbon in this steel. As we mentioned before, carbon can be used to increase the strength of steel, but there is some limitation. If we can add carbon to some extent, because increasing the amount of carbon can reduce the resistance of the steel against corrosion. Because of this concept, they came up with a different new material. It's called stainless steel here, and it's under high alloy. And this steel, we use chromium up to 15% or more. Sometimes we can increase the protection of the material against corrosion. Also, nickel can be used to increase the protection, depending on how much we use, how much we can use chromium and nickel. They have different category in stainless steel that we discuss in the next slides. One major property of stainless steel, or SS, is its corrosion resistance, and also it has a good strength, high strength, and good ductility. Because of the higher strength, sometimes it's very difficult to work with this because we are using chromium and nickel. These steel are more expensive than the low carbon steel. By default, we have three categories of stainless steel. One is called austenitic stainless steel, and then second, ferritic stainless, and martensitic is the third one. Recently, there was another category that was developed. It's called duplex, DUPL EXSS. In austenitic stainless steel, the microstructure or phases is going to be austenite, as it says, and the crystal structure is FCC. In ferritic steel, we have no nickel, it's no chromium and low carbon, and the material is going to be in the BCC crystal structure. And then in the martensitic, we have a chromium, again no nickel, but higher carbon content in it, and the crystal structure is body center tetragonal, BCT. When we are working with duplex stainless steel, we would see two phases: 50% FCC or austenite phase, and 50% BCC or body center cube. Another way to say it, 50% of duplex steel is the ferritic, and 50% of duplex is austenitic. So it's a mix of these two materials, these two steel. And it's strong. This is hard material. Stainless, austenitic stainless steels are used for food and chemical processing equipment, as well as machinery that require high corrosion resistance material. Ferritic steel can be used they have less corrosion resistant property, and also less ductility. They can be used in a kitchen as utensil, up to jet engine parts. Most stainless steel are designated with 3 digits. The first digit, for example 3, shows the general type. 3 represent austenitic, 4 represent ferritic or martensitic. Both start with 4, and then we have 2 that represent duplex. Traditional stainless steel were developed in early 20th century. Since then, other high alloy steel were developed. Some of them are, precipitation hardening stainless steel, which has a composition of 17% chromium and 7% nickel. The strength and corrosion can be manipulated at the elevated temperature. These are some of the material that can be used for aerospace industry. The other one, duplex stainless steel, we already talked about it. This material has resistance to stress corrosion cracking. It can be used for heat exchanger, wastewater treatment plant, as well as pumps. The next class is tool steel, which are highly alloyed steel designed for cutting tool and die and mold. They must have high strength, hardness, and hot hardness, as well as wear resistance and high toughness in impact condition. And these steel have to be heat treated in order to have this high strength or hardness property. The next class of alloys, ferrous alloys, is cast iron. Cast iron has a carbon between more than 2.1 weight percent, but normally up to 4% is the some range that we use in the industry. And the amount of silicon is going to be between 1 and 3%. We have 4 different type of cast iron. The most important one is gray cast iron. Also, we have white cast iron, malleable iron, or ductile iron. In the cast iron, what happens? We have graphite flake that is going to be distributed, uniformly during solidification. Then, because of this, carbon graphite, we have a gray color. Then this graphite has some benefit. For example, the first one is a good vibration damping, and also it has a good internal lubrication. And the third one is a low ductility. Because of these 3 advantages, we can use this material for automotive engine block, or motor housing, or machine tool bases. Here are some takeaway points from this lecture. The carbon content for a steel ranges from 0.02 weight percent up to 2.11%. The common alloying element in low alloy steel is chromium, manganese, molybdenum, nickel, and vanadium. Chromium is a predominant alloying element in all stainless steel. It increases corrosion resistance of the steel. As you remember, austenitic was not stable at room temperature. The reason we use an austenitic name for austenitic stainless steel is that when we add nickel, it can enlarge the austenitic temperature to room temperature. This is the iron carbon diagram. As you remember, this is the eutectoid point. Then we had this gamma phase that was stable at 700. But what happens when you add nickel, this curve can come down to room temperature, 25 degrees Celsius. So this curve is going to be shifted toward the room temperature. So the austenite is going to be stabilized up in room temperature. Nickel is called austenite stabilizer. The next takeaway is that the gray cast iron can be used automotive engine block because of its 3 benefits. It can absorb the vibration. It can be used, it has a good lubrication property, and it has a low ductility.